Hello and welcome to this manufacturing process technology part 2 module 22. We were talking about how to design the electrolyte flow velocity in an ECM process, and for doing that I would like to assume this following. So, we have now a tool and a workpiece as has been shown here, and we can assume that we have let us say the electrolyte entering the system from this direction at the 0 y plane and exiting in this from this other plane formulated here at the other end of the tool electrode combination. We assume all the heat generated by the flow of the electric current to remain in the electrolyte. So, let us just write that here. So, assuming that all the heat generated by the flow of electric current to remain in the electrolyte, that is we are neglecting in our preposition the heat flow through the electrodes, which is a big issue because of the high conductivity of the metal electrodes. So, we are neglecting conduction through the electrodes. So, the rise in temperature d theta in passing a length dx of the electrolyte is given by the following: delta Q dot the rate of increase of heat equals to the rate of mass flow m dot times of the specific heat capacity of the electrolyte C E times of delta theta, which is the temperature rise which has happened because of this movement of the electrolyte from one side of the electrode to the other side of the electrode. So, if I wanted to just try to, so let us just write this down here as the amount of heat carried by the electrolyte. So, if we assume this particular section here that we are referring to as a cuboid, where this really is the face across which the heat gets transferred. So, that is the area. And if you assume that the equilibrium gap, the gap at a point of time t where we are considering this heat transfer to take place is y. Okay. Further, we are assuming a dx element width in this particular case at a distance x from one side where the electrolyte really enters, or maybe one side of the electrode you could consider. So, here if we assume the width to be, let us say, because it is a one dimensional case, we are just assuming the width here to be unity. So, this is 1, okay, whatever be the units. So, it is just a one dimensional case, but in any event you can also assume L, it does not really matter, it cancels out later on in the analysis. So, here the heat release per unit area is given by delta Q dot equals m dot C E delta theta, as you know, m dot being equal to y times of 1 times of the velocity of the electrolyte flow. Let us assume the electrolyte is flowing at a constant velocity V e, okay, times of the density of the electrolyte rho e times of specific heat capacity times of delta theta. Okay. So, you can think of the heat. So, this is the amount of heat carried by the electrolyte, and you can say that the heat release per unit area of the electrode is just dividing this with respect to the area of the electrode which is involved. In this particular case, it is dx into 1. Okay. So, that is how you can predict the amount of heat that comes into the electrolyte. So, let us now try to keep this as such, the total amount of heat rate that the electrolyte is carrying represented in equation 1, and let us now try to find out the electrical power due to the I square R, or you can call it joule heating. Okay. Dissipated per unit area. So, obviously, I is the current, and R is the resistance of the medium. So, I square R in this particular case can also be referred to as J times of dx times of unity, which is the area square. Okay. Obviously, J is the current density, which is current per unit area, and if you look at in the previous example, as the current is coming in this direction from the electrode, the total area that is being considered here is really this dx times of unity, or dx into 1. So, that times of the resistance, which is 1 by conductivity times of the distance of both electrodes across which the whole current is flowing. The current actually, just let me recall, flows from this face, the top face right here, to the bottom face, this distance being y. The total length the current would take, or the path length of the current, is y, and obviously the area across which the current is flowing is dx into 1. So, we can compare this, or we can write it as rho, which is 1 by conductivity times of length of movement of the current y divided by area, which is dx into 1. So, that is how you can develop the I square R heat dissipated, and if I wanted to look at the final values, it is j square dx by k times of y that we are considering. And so, obviously, the heat dissipated of the electrode is going to no other means but into the electrolyte medium, and is being transported by the electrolyte medium. So, if we assume these two heat rates to be equal, so this is the rate of dissipation, you can say, the dq by dt. So, the electrical power which is also nothing but the heat added, if we assume that there are no other conversions of heat. So, whatever power is basically applied gets converted into heat. So, this q dot, or rate of change of heat or rate of transfer of heat, is basically related to I square R in that case. So, which is given by this j square dx by k y, and you already know that this heat is getting pumped into the electrolyte, and the rate at which the electrolyte is being heated is given by y v rho e c e delta theta. So, this is just a complete sort of a, you can say, power balance between the electrical power and the way that the electrolyte is being heated up. And if we just convert this into more realistic equation, we can have j square by k times of dx times of y equals y v rho e delta theta. Let us cancel this y, or d theta can be represented as delta theta or d theta can be represented as square of j times of dx divided by k v rho e C E, where rho e is the electrolyte density, C is the specific heat capacity, J is the current density in the medium, K is the conductivity, and V is basically the electrolyte flow velocity. You could call it VE, okay, in this particular case. So, having said that, now I would like to just seek your attention to the fact that conductivity K really, and so does the resistivity, is not invariant with respect to temperature, because if you increase the temperature, obviously the conductivity is going to be changed substantially. And so, in this event we could actually write the temperature dependence of conductivity as below. Where K can be recorded as K0 1 plus alpha theta minus theta 0, okay, where K0 obviously is the room temperature value of the conductivity, and theta 0 is the room temperature, theta is whatever is above the room temperature, the temperature above the room temperature. So, theta minus theta 0 is the differential, okay, temperature differential, and alpha is basically the specific conductivity per unit temperature, what would be the rise factor associated with K0. So, if we wanted to now solve this equation between, let us say, 0 and delta theta from one side to the other side of the whole electrolyte transfer process as it gets into the interelectrode gap and goes out. Okay. So, this can be recorded if we assume this length here right here to be L, as you can see, the whole length of the tool surface, tool electrode surface. So, I can easily allow this to be converted into 0 to L j square dx divided by K0 1 plus alpha theta minus theta 0 times of rho e C E V. In other words, the velocity of the electrolyte V E can be written down as j square L divided by K0 times of delta theta plus alpha by 2 times of delta theta square times of rho e C E. So, that is how you can find out what is the velocity of the electrolyte V E in this particular case. So, if the gap is y between the electrodes, and the viscosity of the fluid flowing between the electrode or the electrolyte, you can say, is eta, the total pressure required assuming a turbulent flow behavior to maintain a flow velocity V is given by P equal to 0.3164 rho e V square L divided by 4 y R e to the power of 0.25 plus rho e V square by 2. So, obviously, Re here is the characteristic flow Reynolds number. And I can classify these two terms here as the first term signifying the pressure required to overcome the viscous drag, or a better term would be, a better terminology here would be viscous friction between the plate and the electrolyte, moving electrolyte. And the second term that you can see right here, this is the first term, this is the second term, is basically the inertial component. Okay, it's basically the pressure needed to overcome the inertia of the fluid. So, obviously, the first term, because of the scale factor, becomes more significant in comparison to the second term, because the gap is very small and the inertial effects may not be that predominant in comparison to the surface effect, which would happen more in this case. And so, therefore, we would like to predict this value of the pressure that the electrolyte would apply corresponding to a certain velocity. Again, you please record this very carefully, that it is really a function of this V e square, okay, and also somehow a hidden component of velocity within the Reynolds number. So, in a way, this would be able to sort of let us estimate what is going to be the overall pressure rise because of a certain flow velocity that we are introducing in the electrolyte. So, let us actually look at a numerical design example where we talk about designing such a flow velocity within the limits and bounds of the ultimate yield strength of the materials that are being used as electrodes in this particular case. So, let us say that although the pressure acting on the tool face would typically be given by this first term, we assume and we try to find out actually numerically how these two terms would be different. So, in this numerical example, we have an ECM operation being carried out on an iron work piece, and it is so carried out with a square face copper tool using common kitchen salt solution as electrolyte, okay, and they are both having a flat surface and a feed rate of 2 millimeter per minute is used. The DC voltage that is applied is about 10 volts, the total over voltage is 1.5 volts again, and the dimension of the tool face is given out to be 25.4 mm into 25.4 mm. So, it is a square tool face. We also know the boiling temperature of the electrolyte, which is of significant concern in our case. It is 95 degrees Celsius. We should not be able to go to that level. That is how the velocity has to be planned. So, higher is the velocity, greater is the possibility of the temperature to be lower, because the heat transfer now is getting faster. But we have to really limit ourselves to the boiling point, because we do not really want the electrolyte to start boiling because of more heat accumulation and lesser flow velocity. So, there is a trade off, optimal trade off between the flow velocity at the temperature state that the electrolyte would be inside the working zone in an ECM process. So, we find out the total force acting on the tool by this methodology. We have been given some parameters here like viscosity of the electrolyte, density, specific heat capacity of the electrolyte, also the overall conductivity of the electrolyte and the ambient temperature, which is 35 degrees Celsius. So, let us now first compute the equilibrium gap. Which can be given by y equal to lambda by f. So, obviously, lambda can be again calculated by using the expression K A V minus delta V rho z f times of small f. I have already derived this expression many times. So, let us look at what would be the equilibrium gap. In this case, the K value is 0.2 ohm inverse centimeter inverse, atomic weight of iron, we are assuming iron workpiece here. So, 55.85 times of voltage minus over voltage is about 8.5 volts, and this is divided by the density of the iron that we are removing, which is 7.86 gram per centimeter cube, times of the smallest dissolution valency, which is the ferrostate, plus 2, the Faraday constant 96,500 coulomb, and times of the feed rate, which is really 0.2 divided by 60 centimeter per second. So, this much centimeters is what the equilibrium gap is going to be. So, in this case it comes out to be about 0.02 centimeters, okay. And the current density with this gap is going to be J equals K times of V minus delta V by YE. So, in this case current density would be the conductivity 0.2 ohm inverse centimeter inverse times of V minus delta V is 8.5 divided by 0.02 ampere per centimeter square. So, this happens to be equal to about 85 amperes per centimeter square. So, that is how the current density J is going to be. The allowable rise in temperature delta theta is around 60 degrees, because we are operating at about 35 degrees, and we can at the most go up to 95 degrees Celsius, which is the boiling point of the electrolyte. Okay. So, we do not want to surpass this point, because then the finish is lost completely because of the two phase electrolyte coming into the work zone. So, delta theta allowable is about 60 degrees in this particular case. So, this is the condition for flow design. Flow velocity prediction, maybe you can say, and now we want to do that flow velocity V by looking at J square L times of K0 delta theta rho E C. We are assuming that in this particular case, for simplistic sake, the temperature coefficient of conductivity is 0. Although we really in actual case it is not the scenario, there is going to be a finite value of alpha, and conductivity is really going to change with respect to temperature. But just for simplicity in this particular problem, we are assuming alpha to be 0 here. So, in this case, if we provide all the values which have been given to us and calculated in the last step, the value of J for example, which is 85 ampere per centimeter square, times of the value of L, which is actually again if we look back, the area of the face is about 25.4 millimeters or 2.54 centimeters, divided by the conductivity of the electrolyte, which is 0.2 ohm inverse centimeter inverse, times delta theta, which is 60 allowable temperature rise, times of density of the electrolyte, which is 1.088 gram per centimeter cube, times of the specific heat capacity Ce of the electrolyte, which is 0.997. Okay, so that is how the specific heat capacity of a electrolyte is recorded as. So, we are left with now the value of Ve or electrolyte velocity, which is actually equal to about 1410 centimeter per second. So, let us now look at what would be the Reynolds number. So, what is the Reynolds number at this velocity, at this V value? So, the Reynolds number Re is again given by rho of electrolyte times of velocity of the electrolyte divided by the viscosity of the electrolyte times of the characteristic dimension which is twice the equilibrium gap. In this particular case, you have to understand we are talking about a gap which is again y for example here, and 25.4, and this is what is going to continue. So, on one side is the tool, another side is the workpiece, okay. And we want to find out what is the Reynolds number in this cross section right here. So, we already have Reynolds number as 4 times area by perimeter. So, in this particular case 4 times 25.4 times of y divided by the perimeter, which is actually twice 25.4 plus y. So, obviously at equilibrium the y becomes ye. So, I can replace everything by ye, and yv was found out in the last step as 0.02 centimeters, about 0.2 mm. Okay. So, in this particular case if I put 0.2 mm here, so obviously you can approximate this as twice ye, because this kind of 25.4 plus 0.2 is more or less similar to 25.4, and so you are left with only 2 ye. So, the Reynolds number here is having a characteristic dimension given by 4 area above perimeter as twice ye, and if I calculate that with respect to the velocity we just formulated here. So, we have the value of equilibrium gap 2 times of 0.02 centimeters times the density of the electrolyte, which was provided as 1.088 grams per centimeter cube, times of the velocity, which in the current case can be estimated to be 1410 centimeter per second, divided by the viscosity of the electrolyte given as 0.876 times of 10 to the power of minus 5 kg per centimeter second. Actually, we have to convert into gram per centimeter second. So, minus 2 grams per centimeter second. So, that is how you arrive at the Reynolds number here. So, this number comes out to be in a calculation equal to 7004. So, it is pretty turbulent regime in which the Reynolds number is present. So, from the first term of the equation of pressure, of the pressure equation. The pressure equation I have intentionally not derived, because this is a very common formulation found in any fluid mechanics textbook, and so our purpose here was really to devise the flow design, and so therefore, it was not felt necessary that we should go to all the derivations about how this viscous drag or the viscous force or friction can be estimated on a surface. So, from the first term of the pressure equation, the pressure on the tool is found as rho tool equal to 0.3164 times of the density value, which is 1.088 gram per centimeter cube of the electrolyte, density of the electrolyte, times of the square of the velocity. In this case, it is 1410 centimeter square, 1410 square centimeter square, times the total length, which in our case is 25.4 millimeters or 2.54 centimeters, and this divided by again 4 times of the equilibrium gap, which is there, and you can record that as 0.02 times of the value of the Reynolds number to the power of 0.25. So, the Reynolds number has been calculated to be 7004 to the power 0.25, and this is basically the pressure, the total pressure on the tool assuming that the other inertial component is insignificant in comparison to this surface pressure. And this again, if you want to convert into kilonewton per meter square, you have to multiply it by 10 to the power of -4. So, that many kilonewton per meter square is the kind of pressure that we are assuming here. So, in this case it is about 238 kilonewton per meter square, and the force acting on the tool face, if we assume that there is a linear pressure drop when the electrolyte has just entered, the pressure applied by the electrolyte is obviously 0, and on the other side it is a full blown 238 kilonewton per meter square. So, the overall average force that the electrolyte would apply is given by half times of this density, or the pressure, maximum pressure that the electrolyte has applied at the end of the length L, times of the total face area, which is 25.4 into 25.4 millimeters square. Okay. Let's convert this into meter square, and then the total force comes out to be 79 newtons. So, that is how the average force that is there on the electrodes happens to be. So, in fact, we can also calculate what is the average force per unit area, and we can also ensure that that average force per unit area does not go down the yield strength of the material in order to prevent any warping or any damage due to the velocity. So, that is how you can design the velocity of the electrolyte flow in an ECM system. So, in the interest of time, I would like to close on this particular module, but in the next module we will try to look at some more interesting problems related to defects in ECM. Up till then, goodbye.